Hello, hello. Hey everybody, welcome to Deep Talks. I am Erin Lorraine Woodward with the Sanford Underground Research Facility. We do have some seats up towards the front. If you're brave, come grab a seat. If we run out of seats, there are more chairs in the exhibit hall and we can run out and bring some back. So, all right, wonderful. Well, thank you so much for joining us tonight. We do this every month. We have deep talks every single month, and it is one of the ways that we are trying to bring the science that's happening deep underground into the community of Lead and really invite our neighbors in to learn more about that. So thank you so much for being a part of this. Typically, we have one or maybe two researchers here to present about science, but as all of you already know, we have the entire Majorana Collaboration. No, that's a lie. We have over 20 members of the Majorana Collaboration with us tonight, which how many are in the collaboration total? More than 20. 30 or 40. Okay, so a good percentage of them are here tonight. If you're a member of Majorana, can you raise your hand? Awesome. Thank you so much for traveling to Lead to celebrate with us tonight. Yeah, if you didn't hear that, come back in the summer, and it's over 0 degrees, I promise. So hopefully all of our attendees had the opportunity to meet at least one of these scientists and chat with them a little bit during the social hour. If not, there's some time after the presentation if you want to stick around and ask a couple more questions of our speakers or anyone else who just raised their hand, please do. We encourage that. So I also want to take a second to thank our sponsors who make Deep Talks possible. We're sponsored by Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, Edward Jones, and Chuck and Jolene Lichtenwallner. Can we give those sponsors a round of applause, please? Awesome. So tonight we're going to learn about the Majorana Demonstrator and how that experiment can help us understand the imbalance of matter and antimatter in the universe and tell us a little bit about why we exist at all. We have two speakers tonight. Jason Detwiler is the co-spokesperson for the Majorana Collaboration and an associate professor of physics at the University of Washington. He'll be our first speaker tonight. We were going to have a speaker named Julieta Cruzco join us tonight, but unfortunately the weather kept her where she was. So instead, we are lucky to have Matthew Green, who is an associate professor with North Carolina State University, Oak Ridge National Laboratory, and the Triangle University's Nuclear Laboratory. So our speakers, Jason and Matthew, go way back. They studied together and both received their PhDs at Stanford University. And both of them are studying the mass and the nature of neutrinos with the Majorana Demonstrator at SURF and the next generation experiment called Legend. So Jason will be our first speaker. If you could welcome him to the front.
Thank you very much, and thank you, Erin, for the introduction. It's my pleasure to be here. I'm actually really delighted to be here because it was not easy getting here, actually. Let's see, did this go? Oh, yeah, this is the plane I came in on. And unfortunately, Julieta faced a long list of cancellations and couldn't make it. And yeah, so Matt is filling in for her. So thank you very much, Matt, for doing this on short notice. And Julieta prepared the second half of the slides, and Matt will give a perfect delivery, so you're in good hands. Okay, so I want to start tonight by talking about this image that's taken by the Hubble telescope. It's called the Ultra Deep Field Image, and what they did is they pointed the Hubble telescope to a dark patch of sky, I think in the Big Dipper constellation, and they zoomed in as far as they could, and they took a long exposure. And this is what they saw. And this may look like a starry sky, a nice starry sky picture, but actually these are not stars. Each of these specks is a galaxy far, far away. And you see some bigger ones in the foreground. You see some smaller specks in the distance. And it just gives us a sense of how immense and vast our universe is. And this is just one snapshot, right? The real universe is a moving, dynamic system. These galaxies are swirling around each other and interacting. This is a famous image of what's called the bullet cluster, and let me walk you through this. So these purple spots are the spots where you can see a bunch of this. They're like a cluster of galaxies. So there's many galaxies together, and this one has just passed through the bigger one over here, moving at very high speeds. And what we see in this picture is that the galaxies and all of the matter, the mass in these clusters of galaxies have essentially passed through each other. But then in pink, we see some X-rays that were taken by the Chandra Observatory. And those X-rays are from the hot gases that are between the galaxies in these big galaxy clusters. And they've run into each other and heated up, and so we see all this X-rays. And actually, this image shows us that most of the matter in these galaxies, actually I should mention the amount of matter they can estimate based on how it bends the light from the more distant galaxies in the background. It's just really amazing technique. And so there's much more matter in here than we can see in the galaxies. And it's not sort of in this gas and this dust. Actually, this picture is like one of the best pieces of evidences for dark matter, which is being studied by Lux and LZ at the 4850 just down the hall from us. So what I actually really want to talk about is not what we can see in this picture about dark matter. I want to talk about what we don't see in this picture. And what we don't see in this picture is huge explosions of gamma rays. And that's what you would expect if, for example, this was a cluster of antimatter galaxies, and this was a cluster of normal matter galaxies. We can look all around the night sky, and we don't see those sort of matter-antimatter annihilation events occurring anywhere. We've never seen big pockets of antimatter somewhere in the universe running into matter. And that's sort of a conundrum. It's a conundrum because our universe was born in a Big Bang, and we can try to reproduce the early universe. In fact, scientists at Brookhaven National Laboratory in Long Beach, New York, they have an accelerator there called the Relativistic Heavy Ion Collider. And they take nuclei of lead and accelerate them to high speeds and smash them into each other. And it makes this hot nuclear soup. It's called a quark gluon plasma. And it's very similar to the conditions of the universe about 10 millionths of a second after the Big Bang, when temperatures were about 4 trillion degrees. And what happens is we get particles shooting out of this quark gluon plasma, which is like right in the middle. You can't see it. What we see is the tracks of the particles that shoot out of it. And they can analyze all of those tracks and figure out what those particles are. And what we see actually lots of matter and antimatter. In fact, we see one, for every matter particle that gets created, we see one antimatter particle and vice versa. They're created in equal and opposite components. And that's sort of expected because in our laws of nature, as we know them today, all of the processes that we know, that we understand and we have equations for, they treat matter and antimatter on an equal footing. There's no matter-generating processes, okay? Which brings about the question: if we have we haven't seen any processes that create more matter than antimatter, then how do we end up with a universe that's filled with essentially only matter after the Big Bang? So our picture of the Big Bang is a little bit more nuanced. Actually, we do think that in the Big Bang, matter and antimatter were created in roughly equal parts. And it actually only takes about 1 part per billion more matter particles in the early universe than antimatter particles to make things kind of work out. And our picture of what happened is, we had this Big Bang, and one of my favorite theorists, Satoshi Murayama, calls it a great annihilation, that after the Big Bang, as the universe starts to expand and cool down, all of those particles of antimatter find particles of matter to annihilate with, right? They slam together and they turn into light, okay? And so each one of those antimatter particles disappears and takes a matter particle with it, and we have that 1 part per billion excess that was there at the beginning is left over, and that's the entire universe. That's all the galaxies in that deep Hubble, ultra deep field Hubble image, and us in this room as well. So this issue, like how can we get this sort of excess? How can we make enough matter in the universe? That problem was recognized very early on after the initial conjectures about the Big Bang were made. And in the 1960s, this gentleman, Andrei Sakharov, came up with a list of ingredients, like a recipe for how to make a universe filled with matter from the Big Bang. And it takes 3 ingredients. The first one is we need some sort of process that can spontaneously create matter without creating antimatter. Okay? And so, for example, you can imagine if you had 2 photons fly together, we would look for a process that makes, say, an electron and a proton, right? Those are both particles of matter. They're in our everyday universe. And if we had some process like that, if it existed, then that might help us make a universe during the Big Bang. So that's one ingredient, and it goes by the technical name baryogenesis or leptogenesis. Okay, but the thing is, like, there's all these symmetries in physics. If you make a process that can make matter, you're going to have a similar process that's going to make antimatter. Okay, so we're going to be able to slam 2 photons together and get an anti-electron, a positron, and an antiproton if we have this process. By the way, this process doesn't exist. Okay, and yeah, so if we want to get that little excess of matter, then these better happen with different probability. They better happen at different rates. It has to be more likely that you get this process than that one. And that goes by the name C and CP violation, charge and charge parity violation. Those technical terms are not important. Okay, another thing is, in physics, if you can run this process in reverse, and you can get your proton and electron. If this process occurs, then a proton should be able to hit an electron and then disappear again and turn into photons. Okay? So if you don't want to erase any matter that you made by having the inverse process happen, then yeah, we need to have the matter creating processes happen more often than the matter annihilating processes, and that goes by the technical name thermal non-equilibrium. Okay, so of these, so thermal non-equilibrium is kind of an easy one. That we see thermal non-equilibrium all the time, and that's not a problem. C and CP violation is kind of an iffy subject. So we do see cases in particle collisions and making very rare particles where we see matter and antimatter sort of acting in slightly different ways, and that tells us that there's some of this CP violation, but it's not quite enough. It's very difficult to make. In fact, it's impossible still, I think, to make a model of the Big Bang that can create a matter-filled universe that we need for our existence with the amount of CP violation that we see in our current models. And that's the Dune project, I'm sure many of you have heard of it. This is their key science goal, is to hunt for more CP violation to try to see if we can find enough CP violation to make this, make our cosmos work. Okay, but what I'm focused on, and our project is focused on, is this first one, which is, there's really no good solution right now. We don't have any processes that spontaneously create matter in the way I described. That 2 photons gives you an electron and a proton. That we've looked for that. It doesn't happen. Okay, so yeah, we have to look for in more darker, stranger corners. And so we turn to our favorite particle, the neutrino. It might be able to help us out here. So this crowd, I'm sure most of you are familiar with the neutrino, but most of humanity is not. Actually, I didn't really even know what a neutrino was until I was with this guy in graduate school. Maybe the year before he arrived, I first heard of the neutrino. There's a really good movie where the neutrino plays a great role. 2012, and one of the movie characters described the neutrino as minuscule mass, no electric charge. They pass through ordinary matter almost undisturbed. Okay, and as a result, this particle is not part of our everyday lives. If you're not at my house, you're probably not talking about it at the dinner table, and yet actually it's one of the most ubiquitous particles in the universe. So in flying through space, we have light coming to us from distant stars. we have light from the Big Bang reaching us. There's lots of photons zipping around through space. And for every 3 photons, there's about 1 neutrino. Most of those are neutrinos that were born in the Big Bang and are still flying towards us from far, long ago. But there's other nearby sources of neutrinos, like our own sun. So the sun makes neutrinos via hydrogen fusion. So the sun, at the center of the sun, it's mostly a big ball of hydrogen. And the crushing gravity at the center of the sun can press the hydrogen nuclei together and fuse them into deuterium. So one of the protons turns into a neutron and makes a deuterium nucleus. And in the process, it makes an anti-electron, a positron, and a neutrino. Okay? And so the sun is glowing in neutrinos just as it's glowing in light. And we know it's glowing in neutrinos because those neutrinos from the sun can come to us on Earth and cause reactions and nuclear processes that no other particle is able to create. And one famous example is neutrinos can come and hit a nucleus of chlorine and turn it into argon. And in the process, the neutrino turns into an electron. Okay? And as many of you know, this is exactly what Ray Davis did. This is just an incredible experiment. He got 100,000 gallons of chlorine cleaning fluid together in this big tank. And these neutrinos, so they interact very rarely. But if you get enough neutrinos, and the sun is making gobs and gobs of neutrinos, okay? If you get enough neutrinos, then you can make a few dozen atoms of argon in this giant tank per month. It's just an incredible feat of scientific science and technology that you could, just imagine how many atoms are in that giant tank. And he found a few dozen a month. So he was definitely deserving of this Nobel Prize in 2002. So we have detectors now that can not just tell us that a neutrino from the sun arrived, but actually can point back to the neutrino, point back towards the source. And when the Super Kamiokande experiment did this, the neutrinos pointed back towards the sun, and they made a picture. So if you had neutrino eyes, this is what the sun would look like to you. And it's thankful that we don't have neutrino vision because it's very blurry. The actual size of the sun is like 1 pixel here. Okay? So anyway, that's a fun fact about neutrinos. Okay, so I want to talk about neutrinos versus antineutrinos, because this talk is all about matter versus antimatter. So the particle that we call the neutrino, we call it the neutrino because of what happens here in this interaction, say, with chlorine. So when the neutrino hits chlorine, chlorine becomes argon, and the neutrino turns into an electron. The electron is a particle of matter, and so we kind of want to say, oh, a particle of matter must have come in here to give us a particle of matter here. So this one gets labeled the neutrino. The antineutrino does essentially the opposite. So in the antineutrino, it can hit a hydrogen nucleus, a proton, okay? And it can turn the proton into a neutron, and the antineutrino turns into a positron, okay, or an anti-electron. And so this particle that comes in here and it gives us this reaction where this antiparticle comes out here, we call that the antineutrino. And actually, this was the way neutrinos were first discovered. It turns out that nuclear reactors make lots and lots of antineutrinos. And you can put a detector here that's capable of measuring those positrons and neutrons that come popping out of that reaction in hydrogen. And that was done by Cowan and Reines in 1956. And that was also a Nobel Prize. But one thing that we know is that these neutrinos that come out of a reactor are not neutrinos. They can't give us this reaction of turning chlorine into argon. And we know that because actually Ray Davis took his experiment, actually an early version of his experiment, and put it next to a reactor. And he didn't see any extra argon. So he really did that. And so we know that the particle that comes out of the reactors is different from the particle that comes out of the sun in some key way, and one creates electrons when it hits matter, and the other one creates anti-electrons. And that's why we've labeled them neutrino and antineutrino. Okay, in the years that have gone on since, we found out some very interesting new facts about neutrinos. We found out that the neutrino and the antineutrino are distinguished in a very special additional way, and it has to do with the way they spin as they're flying through space. Okay? So it turns out that all neutrinos are what we call a left-handed particle. So it's like if you take your left hand and you point your thumb in the direction the neutrino is traveling, the neutrino is always spinning, and the direction of its spin is the direction that your fingers on your left hand curl. Okay? And if you do the same thing with your right hand, your fingers curl the wrong way for the neutrino, but your fingers curl the correct direction for the antineutrino. Most particles aren't like this. The electron, it can spin in either direction, whatever direction it wants. But neutrinos have this property that all neutrinos are left-handed particles, and all antineutrinos have this right-handed spin relative to their direction of motion. And that brings up actually a new possibility that perhaps the neutrino and antineutrino, we've labeled them this, but maybe they're just the same particle spinning in two different ways. And the spin is what determines how it interacts with matter and whether it creates an electron or a positron when it hits matter. Actually, this was conjectured long before neutrinos were ever even discovered by Ettore Majorana, and it's where our project gets its name. Okay? He came up with this idea, and it was like a crazy crackpot idea at the time. But now we're all thinking he was maybe onto something. So a consequence of this is the neutrino, it would be this special type of particle that doesn't really have a difference between the particle and antiparticle state. And actually, if that's the case, we say actually the neutrino and the antineutrino are kind of the same particle, and they could possibly self-annihilate, okay? Or they could annihilate each other in processes like I showed you before. And in doing so, as I'll show you, they can hopefully mediate one of these matter-creating processes that might help us understand why our universe is made of mostly matter. Okay, and so I'm going to show you what I call a little bang. So the Big Bang created all the matter in the universe. This little bang is going to create a little bit of matter in a single nucleus. And we're going to start with the nucleus germanium-76. I've colored neutrons in red and protons in blue. And what can happen here is, so one of these protons can change into a neutron and emit an electron and one of these particles that we called an antineutrino. Okay? And then in a second, and that's called a beta decay, in a second beta decay, we emit another one of those. And now the germanium-76 has turned into its second neighbor on the periodic table, selenium-76. And if the neutrino has this property, then it's possible that they will annihilate each other. And what we have then in that case is, before this process started, we had 76 neutrons and protons. And after, at the end of the day, we still have 76 neutrons and protons, but we have 2 new electrons. Okay? So in this tiny, tiny event, we create 2 new particles of matter and no antimatter. And we say it's mediated by the neutrino. And it can only happen if the neutrino has this ability to self-annihilate. If the neutrino has this property that the neutrino and the antineutrino are the same particle. And so this is actually not just a wild guess from somebody almost 100 years ago. It's actually like all of our theories are pointing us towards this and saying like this might be a real thing. So the unification of all the branches of physics has been like this long historical trend. And right now we're here at this sort of grand unification scale. Actually, let me walk you through this because this is just like an amazing summary of physics. So, Newton united terrestrial gravity and planetary motion, and his unification of that gave us like the steam engine and the Industrial Revolution and physics as a proper science, a scientific subject. And then electricity and magnetism, those used to be totally separate phenomena, and they were united in electromagnetism by Maxwell. And that gave us, motors and radio communication and harnessing electricity. And then, Einstein merged Newtonian gravity and formulated his theory of general relativity that gave us our understanding of the cosmos as it is today. It led to the space age, the atomic age. And then quantum mechanics and quantum field theory, like our most recent theories, brought together electromagnetism and the weak nuclear force. Like first we found the weak nuclear force, and then we figured out how to merge these two together. And this unification was like just completed with the discovery of the Higgs particle. But yeah, the advances made along the way have given us like the computing era, the quantum era. And so now we're here, and we think that the electroweak theory and electroweak force and the strong nuclear force are sort of two facets of some larger force. And the theories that work, many of them predict that the neutrino is this exact kind of particle. So we think that that searching for this double beta decay might be sort of one of the keys to unlock what's going on at grand unification. And I'll just mention we still don't know, we don't have a good way of how to unify these quantum mechanical forces with our gravitational forces, and help is wanted there. And so if you have some ideas, let me know. I'll share the Nobel Prize with you. Okay, but those grand unification theories, they also, the source of matter creation and the source of double beta decay in those theories is enough to fix these models of the early universe, and Sakharov would be very happy that his recipe would be complete. And I didn't really even have time to talk about it, but the same theories can also give us explanations of why the neutrinos are so much lighter, which is so much lighter than, say, the electron or the proton, all these other particles, which is another like famous problem in physics. So we're like maybe answering 3 disparate questions with one answer, which makes us feel like we're kind of on the right track of something. And all of these predict that this double beta decay should occur. And I'll just end by saying that actually, in our collaboration, we're experimentalists. And regardless of these theoretical motivations, to us it's also just exciting just to go put this device together and try to search for something that nobody's ever seen before. It's exciting in its own right, and it would be fun to be the first people to do it. So with that, I'll hand it over to Matt to talk about how we went about trying to search for this process with the Majorana demonstrator.
All right, thanks, Jason. All right, so we have identified a process that we can investigate, we can look for, that will help us, show that there are matter-generating processes in the universe, and along the way tell us that neutrinos and antineutrinos are the same particle. So how do we actually go about measuring it? That's what the last half of this talk is going to be about. All right, so Jason gave an introduction to this process on the right, in which, is that a laser? Yeah. In which the 2 antineutrinos emitted from this decay find each other and annihilate, or effectively move from one of these neutrons to another neutron in the process and aren't emitted. This process here on the left also occurs, in which you have 2 effectively run-of-the-mill beta decays occurring at the same time in the same nucleus with 2 antineutrinos flying away. We've actually seen it in a handful of nuclei, and it's a standard model process. It's not the matter-generating one. This one on the right is really the one that we're interested in, and it's the one that's indicative of new physics. Okay. The issue is that if neutrinoless double beta decay exists, if it occurs, this process on the right, it's extremely rare. And for us to understand that, we have to quantify a little bit about what it means for a nuclear decay to be rare, how we measure it. Physicists use a term called half-life. And for a radioactive process, half-life refers to how long it takes for half of the radioactive atoms in a sample to decay. But equivalently, it's a measure of how probable it is, if you have one atom, that it will decay in some amount of time in the future. All right, so how rare is neutrinoless double beta decay? Our universe is 14 billion years old, give or take. At present, we know that neutrinoless double beta decay has a half-life in excess of 10 to the 25, on the order of 10 to the 26 years. If we were to grab one atom of germanium-76 and we were to wait for it to decay in a neutrinoless double beta decay event, we might have to spend 10 quadrillion years, 10 quadrillion times the age of the universe in order to have a perhaps 50-50 chance that will decay. It's not the most effective method by which you might try to observe this process. Rather, you want to use a large number of atoms, all collected, and look to see if you can observe maybe just one or a handful decaying in some reasonable amount of time. For example, the number of atoms of germanium-76 in a kilogram is about 10 to the 25. If you get a kilogram of atoms together and you watch it for a year or so, you might be able to see something that occurs with a half-life of 10 to the 25 years in one of those atoms. If you watch for a couple years, you might see something on the order of 10 to the 26 years. It's really important then to have a large number of atoms and to be able to be sensitive to seeing just one or two or maybe three of them decay in some reasonable amount of time. All right, so if you're only going to see a few events maybe in your sample, you need to be real sure that the events that you saw are actually the neutrinoless double beta decay events that you were looking for, and not some other process that might give you a signal that looks similar to it. You also need to be sure that if there are only a few decays happening, that you are going to detect them and you are going to identify them with high efficiency. If you're only detecting 1 out of 100, you need a detector that's 100 times larger in order to be effective. You also need very low rates of things that could fake that signal. Unfortunately, we live in a world, well, maybe fortunately, I'm not going to make judgment statements about it, but we live in a world that is full of radioactivity. That when the Earth was formed, it was included some radioactive isotopes with extremely long half-lives, tens, billions of years. And a lot of them are still around today, occasionally decaying into other things that are radioactive, producing radiation. And so that radiation is around us, and we need to be able to make sure that the events that we are seeing are not some background events from the radiation that exists around us in our lives. All right, so what do we actually look for when we try to measure a neutrinoless double beta decay event? First, let's take a look at this process over here on the left. If this process, this standard model process that's been observed a whole bunch of times, when this occurs, we have 4 products leaving the nucleus, and they're all sharing energy associated with this decay. That this nucleus has changed from a more energetic nucleus to a less energetic nucleus, and that energy difference is getting emitted in these 4 particles. In practice, these neutrinos are going to fly out of your detector, they're going to fly through the Earth, they're going to travel on their way out of the solar system. You have no chance at actually detecting these neutrinos in one of these rare events. These electrons, however, you can detect, and you can measure things like their energies. And if you do that for a repeated decays, what you will find is that the energy that these electrons have is different from event to event. Sometimes they have more energy, sometimes they have less. There's no way to predict it in advance because these neutrinos also have energy, and they are well on their way to Mars by now. And they have some energy, it varies, and so the energy that's left over for the electrons varies. And so if you measure that electron energies a bunch of times, you get this continuous distribution, where sometimes you get a lot, sometimes you get a little, most of the time you get something in the middle, but it's always kind of in this band. In this neutrinoless mode, however, there are no neutrinos carrying away extra energy. All of the energy associated with that decay is going into the electrons. And so if you measure the total energy in the electrons, you will get the same value every time. And it's that energy difference between the two nuclear states, between the more energetic nucleus and the less energetic nucleus. And what we see, perhaps, or what we would like to see, is a tiny little bump down at the end of this large continuous spectrum associated with a few events that all have exactly the right energy for this process. And that would indicate to us that this neutrinoless double beta decay, this matter-creating process, is actually occurring in our sample. So what are some of the backgrounds that we have to contend with? As I mentioned, we have radioactive materials around us in our environment all the time. Some of them, uranium and thorium and the things that they decay into produce gamma rays. Those gamma rays can travel into a detector and deposit just the right energy to make it look like a double beta decay event. Radon is a radioactive gas that actually comes from decays of uranium and thorium. And because it's a gas, it has a way of seeping out of rocks and into spaces where you might have a detector. And sometimes that radon will decay in a way that emits an alpha particle that we might have to deal with. And of course, there are cosmic rays coming in from space. Those cosmic rays are bombarding us. If we had a detector at the surface of the Earth, it would be overwhelmed by those cosmic rays. But also, they have a funny habit of turning materials that aren't radioactive into radioactive ones. And we'll get into that in a little bit. All right, so these different types of, our signal and our different background particles have different signatures in our detectors, perhaps. In our double beta decay events, we have electrons, and those electrons will move about 1 millimeter inside of our detector, inside of a detector of germanium. Gamma rays can travel through materials a bit better than electrons can. They can deposit energy in multiple locations also, spaced perhaps several centimeters apart. Alpha particles from, say, radon tend to deposit their energies on detector surfaces because the range of an alpha particle in our material is something like 1/100th of a millimeter. And so they can't make their way into the middle of a detector. They all get stuck on the outside. And then muons coming in from cosmic rays will barrel all the way through the detector. They'll leave a swath of chaos in their wake and have a very distinctive signature. And we can use these different types of event shapes in order to distinguish between them and help us reduce our backgrounds. In the end, what we hope to see is basically a plot of energies that looks like this, where we build a detector, we measure energies of events over time. We have a batch of events over here at kind of lower energy from that standard model measured 2 neutrino double beta decay process. There's a big, huge hill over here that is not in this plot, and we're just seeing the tail end of it right down here. And then we have perhaps a flat background from those gamma rays, maybe alpha or something in here too, but relatively sparse, so that when we have what looks like 4 or 5 events at exactly the energy that we care about, we know that that is indicative of neutrinoless double beta decay occurring inside of our detector. And it's a signature for a matter-creating process. All right, so we built the Majorana Demonstrator to look for this. We built it here at the 4850-foot level. So Jason and I on our way to so we go underground, to shield ourselves from the cosmic rays. We use the mile of rock above our heads as shielding. We made our way down the Yates shaft when we were building Majorana. The Ross is used now, and into the Davis campus. Our experiment we constructed inside of a clean room. It's a class 1000 clean room in order to limit the dust that might make its way onto our components. That dust has trace amounts of radioactivity in it, and so we keep that dust out. And crucial to this was the tireless work of Robin Varlin over several years, who kept this space as clean as we needed it to be, and we really appreciated all the work that she did for us. We needed to build the experiment out of some of the most radio pure, that's lowest radioactivity materials that exist on Earth. We developed a process to produce copper that is extremely low in trace uranium and thorium by taking commercial copper nuggets, some of the cleanest that you could buy, effectively dissolving it in acid and plating it out onto these stainless steel drums, leaving those impurities behind. Cosmic rays can turn that copper radioactive. It can produce small amounts of cobalt-60 in that copper. And the growing process is so slow, it takes a year, roughly, in order to get a layer of copper thick enough, say a ½ inch thick, so that you can make some widgets out of it. That's the sort of thickness that you need in order to make some parts. And because it takes so long, if we were to do it at the surface, cosmic rays would turn it radioactive to a point where we wouldn't be able to use it by the time it was done. And so we had to grow that copper underground at the 4850-foot level. We had to keep it underground in order to make parts out of it. So we have an underground machine shop where we produced all the copper components. And key to this was Randy Hughes, who spent essentially full-time underground for roughly, I think, 3 years, producing all of the components that we needed made out of the electroformed copper in our machine shop. Once parts are fabricated, we have to clean them, and maybe a few times over again after that, in order to eliminate any surface contamination, any trace amounts of radioactivity on the surfaces. So we have an underground chemistry lab where we would clean up all of our parts, and then we'd store them all in sealed boxes that were purged with nitrogen to keep radon out so that we wouldn't get some radioactivity on those parts that we made. And every component in the demonstrator was treated with that level of care, from the lead stack that weighs more than a 737 to the tiny little pins made out of plastic necessary to keep our electrical signal cables connected to the parts that we needed. In order to keep radon and dust that might be present in our clean room off of our parts, we did all of our assembly of our detectors inside of these glove boxes that are purged with nitrogen gas. In this photo, I am wearing no fewer than 4 pairs of gloves. It was an ergonomic nightmare, but we got it built as cleanly as we possibly could. Yes, it is a challenging work environment. Sometimes you need to be creative in order to work within the restrictions that we had. Okay, so let's talk a little bit about the sort of the way that this experiment is constructed. At its source, or at its heart, we have these high purity germanium detectors. They're called PPCs. It's a technical term for the type of germanium detector it is. But these detectors are made out of germanium material that's enriched in germanium-76, the isotope that can possibly undergo this decay. So we enrich it in that isotope to get as many atoms of that isotope as we possibly can into each one of these little chunks of germanium. And then we use that chunk of germanium as the detector. So that chunk of germanium is both the source of the decay and the detector that we use to measure it. We place them in these low mass mounts made out of our ultra pure copper, and then stack them 4 or 5 tall in what we call strings. We put them inside these vacuum cryostats. Germanium detectors have to operate at liquid nitrogen temperatures, and so we have to cool them down to liquid nitrogen temperatures. And if you want to cool something down to liquid nitrogen temperatures, it better be in vacuum, otherwise you're going to turn it into a snowball. And germanium detectors don't like moisture. So we seal them up in these vacuum cans and we cool them down. We then mount them in what's called a module. So this vacuum can is attached to vacuum and cryogenic systems that are used to operate it. And then we install it inside of this stack of lead and copper that shield us from the radioactivity in our environment down at the Davis campus. And then we surround it with detectors that tell us if a muon actually makes its way through that mile of rock into our lab, because occasionally they do, absorb any neutrons that might be in the environment, and then pump some nitrogen in to keep the radon from making its way in instead. So we use germanium-76. We like germanium-76. It's a good candidate nucleus for this, especially because we can make very sensitive detectors out of this material, out of germanium. Germanium detectors are very good at measuring energies of interactions inside of them. And the better you can measure the energy, the smaller a window you can look in to try to see those events that you care about, and the less background will creep into that window as a result. We also have some methods to help us separate out the events which occur inside the middle of a detector from events that might occur on the surfaces that would come from background. We used in total 30 kilograms of these types of detectors in the demonstrator to get as much candidate nucleus as we could and the best sensitivity for this process as we could produce. Here are some of the ways that we discriminated between candidate double beta decay events and some of these other backgrounds. Double beta decay events all occur in one spot within the detector, and so it really looks like a single energy deposition. And when these charges get drifted through this material from where they originated to this place where the charge is read out, all of that signal arrives all at once. Gamma ray events, on the other hand, can scatter multiple times, deposit energy in multiple different locations within a germanium detector. And when that happens, we see one batch of charge followed by another batch of charge. And so we get a signal that doesn't just look like a simple climb and then a level off, but something that climbs, levels off a little bit, climbs again, and then levels off flat. And so this we can call a background, and this we can say looks like a signal. Events that deposit energy on the surfaces have whole other processes for how they end up generating signal. Charges move very slowly in some places. Sometimes they show up immediately. And the sort of nice, clean signals, like the blue one that we see for events that occur in the middle of a detector, look very different from things that occur on the surfaces that, say, have this very sharp start to the signal, and then take a really long time to eventually level off. Those are two characteristics that are indicative of surface events. When muons find their way through the detector, we have these plastic particle detectors on all 6 sides of the experiment, and so we can identify that a muon went all the way through because it hits some up top, hits some down below. And whenever a muon goes through, it can produce lots of garbage that can also make its way into our detectors and fake a signal, and so we just block out a batch of time around a muon event. And double beta decay event will only ever occur inside of a single detector at once. Gamma rays can hit one detector, scatter, hit another detector. And so if we ever see 2 germanium detectors fire at the same time, we know that that's a background event too. This is what we saw after running the demonstrator for about 5 years. This is our energy spectrum from all of our detectors. And the first thing that you might see jump out at you is this big batch of events right down here. That is the 2 neutrino double beta decay set of events. This decay is one of the slowest decays that has ever been measured, and it makes up the vast majority of our signal. The events that we are looking for live right down here. In this region, we started out with this black curve here, and when we applied our surface event cuts to remove, say, alpha events that occurred on the surface, we ended up with this gray batch of data down here. When we get rid of events that look like they have energy depositions in multiple locations, we go from that gray set of data to the red one. So it's very low in here. And if we zoom in on the window that we care about, this is what we see. This blue peak is the smallest signal that we should be able to reliably detect in the demonstrator if we were to see one. We have this blue curve in here to show us, well, to show you, what the smallest signal that we might be sensitive to would look like. We have all these sort of red events. These are background that tell us we can use to evaluate the likelihood that there might be a background event in this very narrow window where we're looking for our double beta decay events. And this has told us we haven't seen neutrinoless double beta decay events in the demonstrator. From this set of data, we know that it has a half-life of over 8 times 10 to the 25 years. But we are continuing to move forward. Along the way, we actually built basically one of the world's most sensitive radiation detectors across a whole swath of energy ranges. And that allowed us to do a whole lot of other searches for interesting physics beyond neutrinoless double beta decay. Looking for things like dark matter or exotic things like quantum wave function collapse using this very sensitive instrument that we built. And we are moving forward. So here, we built this ultra-sensitive detector using ultra-clean materials and some low background electronics. And while we were doing that, we were in friendly competition with the European collaboration that made some different design choices. They took their germanium detectors. They also used detectors enriched in germanium-76, but they dunked them in a bath of liquid argon. And then they used that liquid argon both to cool the detectors down and as a shielding material that would give off light if background events occur, in the nearby surrounding argon. So you could use it as a way to say, eliminate events where a gamma ray comes in, deposits energy here, and then leaves the detector and then deposits energy somewhere else in the argon. And that was a very powerful technique that they established. And so now we have effectively joined forces to build a next generation experiment that we call Legend. that takes the best of these technologies and combines them into an experiment that will ultimately house 1,000 kilograms of detectors and operate them for 10 years to try to push our sensitivity to detecting this process to 10 to the 28 years. All right, so we are, continuing our efforts to look for this origin of matter. We think the neutrino sector, that this, funny little particle is a great candidate for this. And we are, building more and more sensitive instruments to look for this neutrinoless double beta decay that could answer some questions as to why we're all here. So I'll wrap up there, and Jason and I'd be happy to take any questions you might have.
I don't have a question, I have an instruction. If someone asks you a question, will you please repeat it before you answer it so that our recording will capture the question?
Gladly.
Doug.
You discussed how the neutrinos were produced in the sun, but you said antineutrinos are produced by reactors.
Correct.
So that would be fission reactors.
That's right.
What's the process in the fission reactor that produces those?
Okay, the question is, what's the process in a fission reactor that creates antineutrinos? So in a fission reactor, you start with uranium or plutonium. Usually it's uranium-235 or 238. And fission is like when that nucleus with 235 protons and neutrons, it cracks into two. And when it cracks into two, you have like two different pieces, and it can be like any number of different various nuclei on the periodic chart. But the issue is that those two nuclei are almost always radioactive themselves. And so they have to beta decay and beta decay and beta decay until they become something stable. And so for each fission of uranium, you typically get 6 beta decays to reach stability, and each of those beta decays emits an antineutrino. So that's where they come from. And so they're spewing out of the reactor in all directions. The reactors shine in antineutrinos in the way that the sun shines in neutrinos, but just much more weakly, thankfully. Yeah. Question back here?
What's the draw for using germanium as the element to create these reactions?
So the question is, why germanium? So there are only about a dozen reasonable candidate isotopes for looking for this process. And the different isotopes tend to lend themselves to different detection technologies, right? So, for example, xenon-136 is a candidate. And, like perhaps you're familiar, you can build large liquid xenon detectors like the LZ experiment underground, using xenon as the detector medium. And you can also build large double beta decay experiments where it's both the detector medium and the source. We like germanium for a couple reasons. It has, from a nuclear physics point of view, it has some favorable aspects. But especially, germanium detectors are a really good technology for detecting radiation. And in particular, measuring the energy of an event really, really well. And so we like germanium because we can look in that very narrow window and keep as much of the background that might live on either side of it out of it there, so that we can measure it very sensitively.
Yes,
So, I have 2 questions actually. So, is Majorana complete, and also has there been a location identified yet for legend?
Majorana's.
Repeat the question.
What's that?
Repeat the question.
Oh, yeah, right. So the question is Majorana complete, and is there a location for legend? So Majorana's double beta decay search is complete. But we are doing new searches for physics with Majorana even still, because we built this very sensitive radiation detector, this very low background environment. And right now it's looking for a different nuclear decay that's never been seen before in tantalum. And there was some presentation of initial results on that earlier today. But we will have some exciting new results on tantalum decays before too long. As for Legend, Legend comes in two phases. Legend 200 is under construction and operating now. It's taking its first data. That is in Gran Sasso, Italy. It's in the existing infrastructure where the Goethe experiment, the European experiment, was already operating. We do not yet have a site selected for Legend 1000. That's in process.
Yes.
I was looking at one of your slides there where you're mentioning about the helicity of the antineutrino. No, I was just thinking there. I was wondering, like, we don't consider like time reversals. I was wonder whether, like, under time reversal, is that like the right-handed neutrino is actually the same left-handed neutrino, but looking at minus d-handed?
Yeah, so the question is, if you look at these neutrino and antineutrino and how they're spinning, is a neutrino going forward in time look like an antineutrino going backward in time? Is that the question? And I always have to think very carefully about this, so let me think. So the right-handed neutrino would be spinning like this forward in time, and if it's going backward in time, then I think it would be going like this, right? And if it's going backward like that, I think it's still right-handed. Did I get that right? I think I got that right, yeah. So so in the neutrino case, that antineutrino going back in time would still be an antineutrino. Interestingly. Did I get that right? Okay, my colleagues are nodding. Yes. Good.
You have to hold out your hand. Your left one makes an L.
Yeah, that's how I remember. Okay, next question.
Does the annihilation of these two produce anything?
The question is, if you actually got two neutrinos to annihilate, would it produce anything? And we did kind of a slide. There's kind of a sleight of hand in neutrinoless double beta decay where those two neutrinos come together and nothing comes out of that. That can happen because the neutrino is sort of an internal particle inside of that process. The electrons coming out are sort of helping carry away the energy that the neutrinos would have carried out had they not annihilated. If you just had like two neutrino beams, like a Fermi lab and an anti-Fermi lab over here, and tried to make these annihilation processes, so we would never have a chance of seeing them because they would be ultra rare. But yes, if the neutrinos annihilated, they would make particles that come out of there. And so I guess they would probably make something like a electron anti-electron pair, or maybe a W plus and a W minus, or two Z particles, or you could get any number of particles depending on how energetically you slam them together. Something would have to come out of there. The question is, why wouldn't they make pure energy?
Yeah.
So the energy has to be carried away somehow. So with the neutrinos come in with energy, and if they just disappeared into nothing, then energy wouldn't be conserved. So they have to turn into something that carries away the energy, if that makes sense. Yeah.
Can they turn into two photons?
It's possible that they turn into two photons. In order for them, but it's a little bit tricky because the neutrino doesn't have any electric charge. And electric charge means that it would couple the photons. So, but it's possible that the neutrino has a magnetic moment. And if the neutrino has a magnetic moment, then it could annihilate into photons. And searching for magnetic moments is something that we try to do, that we could potentially do with our experiment. Question in the back?
So I think I learned in grade school or high school that matter can't be created or destroyed. And how does this fit into that if there's more matter being created?
Yeah.
Going in and coming out?
Yeah, so the question was, we've heard when we were young, matter cannot be created or destroyed. So how does that merge with this picture? So that is matter can't be created and destroyed. That is true in all of the known laws of physics, right? But we know that matter was created at the start of the universe, right? This is the entire problem, is trying to answer your question. Yeah. It's a really great question. Energy can't be created and destroyed. Yeah. So even in this the process where I was talking about two photons making matter, they've made two new matter particles, but the energy came from something else. Photons that we don't call matter, they would be one form of pure energy, electromagnetic energy in that case. Yeah.
Thank you so much. I think we need to wrap things up. So can we give our speakers a round of applause, please? So like I said earlier, we do have some time to mingle afterwards, so please take your time as you leave and try to chat with one more scientist before you head out. I'm going to plug next month's event really quickly. So as you know, we don't just do physics experiments. If we did, that would be enough, because this is really cool, right? But we also do biology, geology, engineering experiments deep underground at SURF. And so next month, on March 9th, we are inviting Caterpillar, known as CAT, the construction equipment company. They are doing some research underground at SURF as well. And so we've invited one of their speakers, Daniel Pierce, to come and talk about what they're doing. So if you're more engineering-minded or construction-minded and want to learn a little bit more about that, we invite you to come back on March 9th. And I think that's all I have left. So thank you again so much for coming. We're really happy you're here. So have a lovely